In today's video, we're going to look at graphing functions by translation. So before, in a previous section, we looked at different graphs of functions that were known as like the basic functions, the ones where you should really know what the graphs look like for those particular functions. What we're going to look at now is actually translating those basic functions. So if we do certain things to those functions, what do the graphs look like now? We're going to do both vertical translations and horizontal translations. So I want to discuss both of those, and then we're going to go through a bunch of different examples of the different types of problems that you might come across whenever you do translations. So first thing we have is vertical translations. That is anything where we move the graph up and down. So you take your parent function, your basic function, and a vertical translation will somehow move it up or down or compress it or stretch it, etc., in that y direction. So we're dealing with something that's vertical. A horizontal translation is anything that deals with anything across the x-axis. So it's going to move it left or right, or it's going to stretch it or compress it along that x-axis. First thing we're going to look at is the vertical translations. These are the ones that are a bit more intuitive, okay, and you can kind of see what's happening and why. If we take our basic function, okay, we use x squared a lot in the examples that I'm going to give just because it's an easy thing to see what happens to it, etc. If you took your basic function, let's say f of x is equal to x squared, if I then add some number after it, if that number is greater than 0, then I take my basic function, let's say x squared, and I'm going to move it up by that many units. If c is negative, so I get, let's say, x squared minus 2, I would move it down by 2 units. So if c is greater than 0, that whole graph shifts up. If c is less than 0, it will shift down. So it's just moving it up and down with respect to that y-axis. So that makes sense. If we multiply our basic function by c, so let's say you had something like y is equal to 2x squared, okay? If that number is greater than 1, then you're going to stretch it in that y direction, in that vertical direction, by a factor of c. So if you had 2x squared, you would be stretching that graph by a factor of 2. If c is between 0 and 1, then you're going to compress it by that factor, okay? So we're going to compress the graph. Let's say if you have 1/2 x squared, you would be compressing it by a factor of a half. So you would be shrinking everything down by a factor of a half. If you put a negative in front of it, so if we had negative x squared or negative x cubed or negative x or whatever your basic function was, you just reflect that in the x-axis. So you're literally just going to take what you had and do the mirror image of it across the x-axis. The horizontal translations are a little more counterintuitive, and a lot of them actually do the opposite of what you think they're going to do. So vertical translations tend to do exactly what you would intuitively think that they would do. Horizontal translations tend to do the opposite. Okay. The easy one is reflecting in the y-axis. So if you get f of negative x, okay, so I've taken my basic function, my parent function, and anywhere I see an x, I put a negative x. So I'm dealing with things inside the function, okay? So if I had, let's say, I don't know, negative x plus 2, okay, with my parent function being, okay, I've made the x a negative x, and then I've added something onto the end of it. So by adding 2, I would be moving it up by 2 units. But where I had an x, I've now made it a negative x. So this isn't like our previous one where we just did negative of the whole function. I'm just making any x that I have inside the function a negative x. Okay. So if that is the case, then you would reflect your whole function, your whole basic function, in that y-axis. So exactly the same as we did, but this time we're using the y-axis instead of the x-axis. So we're not making the whole function negative here, we're just making any x inside the function a negative x. Okay, all of these horizontal translations deal with the x inside the function. So we're dealing with inside the function, not the whole function itself. So if I have f of x plus c, so anywhere where I see an x in my basic function, I'm now putting x plus c. If c is greater than 0, well, you would think, because of the way that the x-axis works, that horizontal axis works, you would think that if c was greater than 0, you would move it to the right, and if c was less than 0, you would move it to the left. Okay, just because of how a number line works, you think if c is greater than 0, well, I'm going to move it in the positive direction of the x-axis. You don't. It's actually the opposite to what you think. So if c is greater than 0 in that case, so if you had something like x minus 2 that you're replacing for every x in your function, if you had x minus 2, you would actually shift it to the right, and if you had x plus 2, you would shift it to the left by those 2 units. So it's the opposite to what you think. So if c is greater than 0, you shift it to the left. If c is less than 0, you shift it to the right. So it's the opposite way to what you think. Same goes with stretching and compressing. Okay, if I now replace every x in my function by cx, if c is a fraction between 0 and 1, okay, it's actually going to lead to a stretch. So if I replace every x by, let's say, 1/2 x, I'm actually going to stretch everything by a factor of 2 in the x direction. If I have that c is greater than 0, so if I replaced every x by, let's say, 2x, then I would actually compress it by a factor of 1/2. So you do the opposite to what you think. Whenever you're dealing with things inside the function, it's always dealing with horizontal translations, and it does the opposite to what you think. So if c is a fraction, you end up stretching it. So c is a fraction between 0 and 1, that graph ends up stretching. If c is greater than 1, then you actually end up compressing your graph in that horizontal direction. Same with moving it left and right. If c is greater than 0, when you add c to x inside your function, you actually end up shifting to the left. And if c is less than 0, you end up shifting to the right. So it's always the opposite to what you think. Let's look at a particular example here. So I've got the graph of x plus 3 cubed, and we're going to sketch this graph. You start off with whatever your parent function is. So we can see here that the basic function, the parent function, is obviously here x cubed. Okay. Okay. We can see that that's the basic function, and we've done something to x cubed here. What have we done? We've replaced every x by x plus 3. So inside the function, of y is equal to x cubed, we've replaced every x with x plus 3. Okay. Because of that, we know that we're dealing with things inside the function, therefore we are going to be doing a horizontal translation. Now the question is, what horizontal translation are we doing? Well, we can see from here, I'm dealing with this kind of translation, okay? I've taken my original function and I've added a value to the x inside the function, okay? Now, in our case here, c is greater than 0, c is 3. So that means that I'm going to be shifting to the left by 3 units. So I take my original graph of x cubed. I'm only going to be doing a sketch here. I take my original graph of x cubed, and now I'm going to be shifting it. You can do this on the same graph when you sketch it, but I'm going to be shifting it to the left by 3 units. So now it's going to go through x is negative 3. Okay. we now also have a different y-intercept. Okay, so when x is 0, if I plugged in x is 0 into this function, I would get f of x, my y value, would be 3 cubed. 3 cubed is 27, so it actually goes through 27 on my y-axis. This isn't a very accurate sketch, but it gives you an idea of what's happened here. All we have done is we have taken the original parent function, that basic function of y is equal to x cubed, and we have moved it to the left by 3 units. In our next example, I have the function negative x plus 2 squared minus 1. So here, when we look at what our parent function is, we can easily see that it's x squared. Okay, that is the major function that we are going to be transforming here. And then I've written down exactly what we are going to be doing in order to translate that parent function so that then we can go ahead and sketch the graph. So inside our parent function, you can see instead of just an x, we have an x plus 2. It's inside the function. That means that we are doing a horizontal translation. And we know that if that value is positive, so we're adding a positive value there, we know that that means that we are going to be shifting the graph to the left by 2 units. Then we move to things outside of the parent function. So we've dealt with all of our horizontal translations, we now move on to vertical translations. So we have negative of that function. So because we've got a negative in front of x plus 2 squared, that means that we take that x plus 2 squared graph and then we are going to reflect it in that x-axis. So that's going to give us our first vertical translation. And then once we've done that, we're going to subtract 1, which means we then move down by 1 unit. So work your way out like you would do with order of operations. Deal with anything in the parentheses first, so anything that deals with the parent function inside that parent function. Then you're going to deal with things outside of the parent function. What have we done to it in terms of multiplying things to it, etc. And then what have we added and subtracted to and from it. Okay. So if we go ahead and think about how we would draw this, you start off with the graph of x squared, which should look something like this. We're shifting it to the left by 2 units. So we know that this point here is 0, 0. That's going to be shifted to the left by 2 units. So that point there is going to go to negative 2, 0. So the whole graph shifts by 2 units to the left. Then it's reflected in the x-axis. So then we're going to end up with basically an upside down version of the graph that's been moved over by 2 units. So something like that. And then it's going to be moved down by 1 unit. So when we sketch this, it should look something like this, where this point here should be negative 2, negative 1, from where we've shifted to the left by 2 units and we've moved it down by 1 unit. The next thing I want to do, which is another type of problem that you may get, which is kind of feeding off of exactly what I just did in the last problem, where I looked at what happened to that origin point that I knew existed in the y is equal to x squared parent function graph. What they can ask you is, here is a particular point of some function. What I want you to do is to track that point and tell me exactly where that point would land if it is translated using our new function, using our translations. So in this case, you can see that our parent function is said to be x squared. Then we're looking at the point negative 2, 4, which we know lies on x squared. If you square negative 2, you get 4. Now we want to see what happens to that point when we use this translation. Work from the inside out is my recommendation whenever you do this. Okay, just work from the inside out and try and figure out what translations you're doing, but always start with the inside first. Deal with those horizontal translations first, then we can deal with the vertical ones. So first thing, we start with negative 2, 4. Okay, I would kind of track this out with arrows is my recommendation here. Then the first thing we've done to x is we've subtracted 3. So inside the function, we've got x minus 3. That tells me, using our horizontal translations, because we've got a negative 3 there, we're actually moving to the right by 3 units. So my point negative 2, 4, the first thing it's going to do is it's going to move to the right by 3 units, meaning that my x coordinate is going to change by adding 3 units onto it. So move right by 3. Okay, so that tells me that I then end up at 1, 4. So my x coordinate is going to change by 3 units. Nothing's happened to my y coordinate yet because I haven't dealt with anything vertically. The next thing I've done is I've got a 2 in front of that. So I'm now at the point 1, 4. What does that 2 do? Well, it tells us, using our horizontal translations, that we have this compression that happens. So it's actually going to compress the whole thing horizontally by 1/2. Okay? So what does that mean? It means that every point shrinks by a half factor, telling me that my new coordinate is 1/2, 4. Now, we're going to deal with our vertical translations. These are slightly easier because they do exactly what you think they're going to do. So the first thing we do is we deal with the negative 5. So we've got negative 5 of our function. What does that negative 5 do? We'll first deal with the 5, then deal with the negative, because that negative, all it does is it's going to reflect this thing, whereas 5 is actually going to deal with a stretch of the graph. So I would deal with the stretch first, then I would deal with the reflection. So that 5 is going to stretch our graph vertically by a factor of 5. So that's going to affect our y coordinate. It doesn't affect our x coordinate. Our x coordinate is going to stay where it is, but it's going to stretch everything by a factor of 5 in the vertical direction, telling me I then go to 1/2, 20. Okay. Then the next thing I do is that I know that I'm going to reflect in the x-axis. Okay, so I take my graph that I have and everything gets flipped mirror image in the x-axis. So all of my x coordinates are going to stay the same, but my y coordinates are now going to become the negative of what they were. So I'm now at 1/2, negative 20 when I flip in that x-axis. And finally, I've got +1. That's going to shift everything upwards vertically by 1. Again, just changing my y coordinate. So what have I done here? I've got my original point -2, 4. Then I know I'm working inside out. I'm then going to move to the right by 3. I've then got a compression happening by a factor of 1/2 in that horizontal direction. Again, it will only affect the x coordinate. Then I deal with anything vertical, meaning it's going to affect the y coordinate. First thing I dealt with was dealing with that stretch by a factor of 5 in the vertical direction. Then I dealt with the negative, which flipped it in the x-axis. And then I added 1 and shifted everything up by 1 unit. And this is where that point goes to. My next example is just an extended version of what we just did. So you're given a graph of f below, okay? This is a graph of f and they give you the 4 major points that lie on this graph. You've got 2 endpoints and then a couple turning points where you change direction in them. And it asks you to sketch the graph of this new function where we take our old function and inside the function, so something that's happening horizontally, we are going to reflect in the y-axis because we've got f of negative x. So that's going to start by doing a reflection in the y-axis. That's the only thing that we have to deal with horizontally. Everything else is vertical. It's outside of that function. So then we're going to stretch vertically by a factor of 2, and then we're going to move everything down by 3. And in order to draw this graph, because it's not one of our basic functions that we're used to, you track the 4 major points. So if you are ever in doubt of how to draw something, always look at a major point on the graph, and you can always track it through these translations, exactly like I just did, and like I did before when I looked at the origin on that x squared graph and I tracked what happened to the origin to help me redraw the graph. You can go ahead and do that. So you can always track the major points, and they've tracked all 4 points here, and they've gone through that reflection in the y-axis, the vertical stretch by a factor of 2, and moving the whole graph down by 3 units. And they've seen where those 4 points have gone, and then they have redrawn that graph. So you can see where we've done this reflection, where we've got the stretch and where everything has moved down. So it agrees with exactly what we have done. The last type of problem that you may come across is where they give you a graph and they actually ask you to find the function. Okay? They're never going to give you anything that is crazy, okay? You're always going to get something that is pretty self-explanatory and nothing where you're dealing with a lot of stretches or compressions. It will be something that is most likely just being shifted horizontally and vertically. Just because stretches and compressions, it's actually very difficult to figure out what the function may be when you're dealing with things that have been stretched, compressed, etc., especially in the horizontal direction. So whenever you get one of these problems, 99% of the time it's just going to be dealing with moving things left, right, up and down. So that's exactly what we're going to do here. We've got this x squared graph. We can see already it's a quadratic graph. Okay, and the question is, what is the function that it represents? So we can see obviously it's been shifted. And we can see that instead of the vertex being here at the origin, it is now here at the point -3, -4. So a possibility for our translation here is where we have shifted it to the left by 3 units, and then we've shifted it down by 4 units. That tells me that if I took my original graph of y is equal to x squared, I'll call my new function f of x, if I've shifted it to the left by 3 units, that means inside my function, remember it's the opposite of what you think whenever you deal with anything horizontal, it would actually be x plus 3 squared, and then outside my parent function, I've got -4, I've moved it down by 4 units, which would give me this function. Whenever you do this, my recommendation then, just to make sure that they haven't done any stretches or compressions or anything, is just to check one other point on the graph to make sure that it matches with that particular translation. Like I said, it should be something pretty simple like this, where they have just moved it left, right, up and down. You shouldn't be dealing with any stretches or compressions, but just check one other point on the graph to make sure that that is what the function should be. So I'm going to check one other point on this graph. In this case, you can pick whatever particular point you want that you know is on the original graph, and then see where that point has gone to with your new graph. Okay, so if we take the point, let's say 1, 1. Okay, we know 1 squared is 1, therefore it lies on our original y is equal to x squared graph. Under the translations that I've done here, let's see where that point goes to. Okay, so what I've done here is I've got x plus 3 squared, telling me that this point should be moved to the left by 3 units. So that point then moves to -2, 1. And then it's moved down by 4 units, telling me I go to -2, -3. So first I've dealt with the inside part of the function with that horizontal adjustment, and then I've dealt with the outside of that parent function with the vertical adjustment. Okay. Now, if you actually look at this graph, we can see -2, -3 actually lies on the graph, so we should be all good. But what I would do, just to double check, just in case it doesn't actually show up on the graph and it may be way off, and actually outside of the range of what is given on the piece of paper, just to check, I would plug this point into this equation here to make sure it is actually satisfied. So if I plug in x is -2, I want you to make sure that the number that you get out here would be -3. So -2 plus 3 is 1, 1 squared is 1, minus 4 is -3. So it satisfies our equation. It satisfies the translation that you have done. So you've gone through, you've translated that particular point to give you a new point. If that new point satisfies your new equation that you've come up with, then it's correct. So I would always do that with any one of these particular problems that you get. If you are given the picture of a graph and they ask you what the function is, just deal with moving things up, down, left and right to start with. Come up with what the function could potentially be. Then, just to check it, take a point that is on your original graph, that parent function, move it as you would have done when you've come up with this new function. So here we move to the left by 3 units, down by 4 units. See where that point will go and then check to see if that point that you've come up with would actually lie on your new graph. And if it does, then you have the function correct.